So calculus, we're going to do a very different series of units to finish off our course and talk about vectors. Have nothing to do with derivatives and rates of change, something very different. If you've taken physics, you have a little bit of a heads up, but we're going to be talking about things in a little bit of a different way. I want to introduce vectors as a way that we can solve problems that require magnitude and direction. So for instance, I had to move my piano a while back. Couldn't do it myself. Had some people come in to help me. But what if you guys had wanted to step up and help me move my piano? So the strongest person in the class for sure would be Winnie. So if Winnie were to pull on my piano, and there's Winnie's vector. So that's just showing a direction and a level of strength that Winnie has. So we usually show vectors with a little arrowhead over the name. Okay, there's Winnie. And Cam decides to come and help. Okay, and so if they were working together, that was what their vector diagram might look like. And they would pull my piano very well together. Now, what if instead Mackenzie said she was going to help, but we all know that she's just a little bit, not entirely helpful. She has to do things her own way. So Mackenzie's going to pull on the piano like this way. So the piano's not going to go as straight, perhaps, as it would have if just Winnie and Jacob had pulled. She's going to help, but she's going to kind of pull it in the wrong direction. It's going to go like that. So that's what our vectors are modeling for us. What happens when we have a force or a velocity with a certain magnitude and a certain direction? Other scenarios could be that Liam comes along and he's just like not helpful at all. So there's Winnie and she's pulling away, and Liam comes along and he does this. So there's Liam's vector. And he is not helping. And we know if Liam were to push in the opposite direction, that force would really just be a little force. It would go in the right direction because Winnie is so strong, but Liam would be working against her. So this is the model of the types of things that we're going to talk about, and we're going to use arrows to indicate something with magnitude and direction. So a few definitions to start with. A scalar is a magnitude specified by just one number. For instance, your mark in this class, 99. My age, 29. Those would be things specified by just a number. But a vector, on the other hand, has both magnitude and direction. And that line was poor planning on my part. Both magnitude and direction. For example, the speed of my car this morning is exactly 80 kilometers an hour. That is a scalar. It is a singular number. But if we said I was driving 100 kilometers an hour in a southeast direction, that would be a vector because it has magnitude and direction. This would be a velocity. This is speed, and it's a scalar. So things like speed just has a magnitude. It would be a scalar. My age is just a number, 29, and it is a scalar. Whereas a force has both a magnitude and a direction in which it's applied. It would be a vector. The temperature today is just a scalar. It has no direction. Volume and area would be scalars because they don't have a direction implied. Density is just a magnitude as well. It does not have a direction implied, nor does displacement. Oh, sorry, going too fast there. Displacement is a vector because it does have a direction. And strangely enough, weight is also a vector. My mass is the same on Earth and the Moon, but my weight is not. My weight is a vector because it has a downward force depending on the force of gravity. So we're going to start today with geometric vectors, which can make a lot of sense to our eyes. It is represented by a directed line segment. So the direction in which you draw it indicates the direction in which this force or whatever is going. So for instance, a truck driving away from the school is a vector, and I could draw this as my truck, 100 kilometers an hour, and it is going in a northeasterly direction. We have different notation that I would just like to introduce to you today that we can use for vectors properly. This bottom, don't always put a point there, but that is the initial point. That's where the truck started. We call that the tail. The terminal point, where we put the arrowhead, is called the tip. The notation that we use to show a vector, so if this is vector u, we usually put an arrowhead over top. As mathematicians, we're getting terribly lazy, so you tend to have a letter with like a half an arrow, like that. Some books you will find, they take that letter and they bold it, and that would indicate a vector. Often we see capital letters, so starting point AB, that would be vector AB, and we would use capital letters with that arrowhead over top. The length matters for a vector. Magnitude would be indicated with absolute value bars because that is a distance of vector u. That would be its magnitude. Our foundation for working with vectors is going to be trigonometry because direction implies bearings and degrees and north and south and all of that sort of thing. So we need to get direction in our head. And if you need a review of some basic trig, that would be a great use of your time over the next couple of days. There are two different ways of giving a direction. Well, there's probably many, but there's true bearings, and there are quadrant bearings. Okay. True bearings are what is used by pilots, both air pilots and ship pilots, and it is always a direction from north, and we turn clockwise. So a true bearing of 310 degrees is we face north. We turn clockwise towards the east. That would be 90 degrees. We keep turning, keep turning. Once we hit due south, that's 180 degrees. Keep turning west, that's 270. And a little bit further, that would be 310 degrees from due north in a clockwise direction. Quadrant bearings. start with either north or south, face that direction, and turn so many degrees towards the east or the west. So for example, north 50 degrees west means we started by facing north. We turned 50 degrees towards the west. That would be our vector. Vectors are considered equal if and only if they have the same direction and magnitude. We would consider them parallel. If I go 100 kilometers an hour northeast and you go 100 kilometers northeast, but you start in Fordwich and I start in Listowel, we have different paths, but our vectors are the same. They have the same magnitude and direction. So on my parallelogram here, if we can make sure we see it a little more clearly, vector AB is equal to vector DC. Direction matters, length matters. Vector AD is equal to the opposite direction of CB. We're going to talk today also about adding vectors. If I have vector u and vector v and I want to add them together, these are geometric vectors. I have drawn them freely on the page, so they're free vectors. I can move them all I want. So if I want to add them together, I can have vector u plus vector v. That would be like me traveling from Listowel to Palmerston, having lunch, and then going from Palmerston to Mount Forest. My overall journey really is I went from Listowel to Mount Forest. And so my journey would be taking vector u and adding vector v to it, and I would add them tip to tail. So starting in Listowel, traveling to Palmerston, on to Mount Forest. So my vector addition would be start to finish. So this would be vector u plus vector v. Where did I start? Where did I finish? And vector u plus v has a magnitude and direction. If, however, I had decided to add v to u in that order, vector v plus vector u, I would have a vector that looks the very same as the u plus v that I drew a moment ago. See if I can draw straight, though that's the problem. So vector v plus vector u has the same magnitude and direction as vector u plus v. That tells us that vector addition is commutative. The order doesn't matter. So this is called the parallelogram law of vector addition. I'm going to try and draw a diagram. So if you have vector u plus vector v, and you add them together, u plus v, that would be the same as vector v, I'm trying to make them parallel, plus vector u, okay, parallelogram law of vector addition. It is commutative. The order doesn't matter. Maybe a clear way to write it. is that u plus v, vector u plus vector v, equals vector v plus vector u. It does start to get interesting if we're trying to look at this in 3D, so do the best that you can. But if I have vector AD, so that would be at the front of this parallelogram, so from A to D, direction matters. And then I'm adding vector DH, so I start at D, I end at H. So I'm going from front corner back to the back corner. That would be the same as starting at A, because that's the start of my journey, and ending in the very back top corner. That's the same as starting at A, ending at H. The second one, I am starting at A and going to B, so that's my first vector, AB. And then after that, I'm adding to that vector BF. Vector BF starts in the front and goes back to the back. You can see that in 3D. And lastly, I'm adding to that vector FH, which starts in the back corner, goes to the top. Plus F, oh, I'm sorry, FG, not FH. Wrong vector. FG starts in the back and goes to the back corner. So all in the back there. Vector FG. That is the same vector as starting at A and ending up in G. So my final result would be vector AG. The third one is vector AE, so from front to back at the bottom, and adding to that vector HC, starting at the back, going to the front. Well, vector HC is the same as vector EA. It has the same magnitude and direction. So that's like starting at A, going to E, returning back to A. So we haven't really gone anywhere. So that ends up being the zero vector. The last one is interesting, AD, so going upwards. And then AE is like going backwards. And AB is like going to the right. So if I do AE first, AD first, and then instead of drawing it as AE, I draw it as DG because that's the same vector. And the third one, instead of drawing it as AB, I draw it as GH because those are the same vectors, same magnitude, same direction. Then my final result is starting at A, ending at H.